Hello, I made a video last week where I tested a bunch of GPS modules and made some charts to see how well they performed compared to each other. But unfortunately I made a bit of an oopsie, quite a large oopsie actually, like 2 orders of magnitude oopsie. And I first started to think something might be a little bit odd when I saw these values coming in from the GPS, and there weren't very many unique values. So you can see this is for the 7M, I think it was, or the BN220 maybe, but this is the entirety of the unique values that we got. And also when we look at these heat maps, they are pretty coarse. There's not much fine detail in them. The fact that these pixels, let's call them, were elongated, I wasn't too surprised that they were elongated, but I didn't expect them to be that elongated. And another thing that was a little bit weird was that when we look at the difference in fluctuation between latitude and longitude, so that's latitude there, see it's moving a lot, I mean it's moving often by small values, and then if we look at the longitude, it's moving not so often but by slightly larger values. So there were a number of things that didn't quite sit right, but mostly I put it down to the fact that I'm down here at the bottom of the world in New Zealand, where there are less meters per longitude degree. And in fact I mentioned something about that, but I also mentioned what's up with that, in the fact that the elongation was the other way around, like basically this difference in fluctuation was the opposite to what I would expect if this was caused simply by the fact that we are down here in New Zealand. So there were some suggestions in the comments of that video about things like maybe satellites moving around could cause it or something like that. But it wasn't until I saw this post by Wizard Tim, something to do with Monty Python maybe, that put me on to the correct answer, which was that I should not have been using single precision floating point numbers. I should have been using doubles. And I don't know why this slipped my mind, because I came across this problem when I was using the RTK modules a few years ago. I had to use doubles instead of floats. But for some reason this time it just completely slipped my mind. So I figured I should probably make a follow-up video using some real results, which is what this video is about. And along the way I improved a few things, like we're using 10 Hertz data now instead of 1 Hertz. I added 2 more GPS modules, so there's 8 in total. The new ones are the Neo-6M and the BN880Q. So we have 4 microblocks and 4 Bayesian modules sort of competing in teams against each other. And the charts that I made now show using units of meters instead of just a lat long number, because there were some comments saying that it would be more useful to see in meters the distances. But before we look at the results, I wanted to dive into the details of what went wrong with the floating point number stuff, because it might help somebody to avoid that problem in future. So I'll put a little time thing on the screen here where you can skip to if you don't want to hear about this. But the first thing I saw here that really set off the warning bells in my brain was this mention here from Tim about 100,000th of a degree not really being that much. And he's perfectly right, of course. If we look at the information provided to us from the GPS module, we'll see that it is a value scaled by 10 to the power of 7, which is 10 million, not 100,000. So there's the 2 orders of magnitude inaccuracy that I was talking about. So this value is not a floating point number, it's an integer. This means it's a signed 4-byte integer, or a 32-bit integer. And so let's take a look at a bit of source code here. So these 2 values here would be what you get directly from the GPS. And to look at that in what we would call decimal degrees, those would be the numbers that it's actually representing. But it's scaled by 1, 2, 3, 4, 5, 6, 7 digits. And the reason it does that is because if it was to give us a 32-bit floating point number like that, it would lose a whole lot of precision. Now, I'm a computer science graduate, so I really should have been keeping this thing in mind a lot better than I was. But what happens when you use a floating point number is you only get, it says the total precision available is only 24 bits, because you're using up 8 bits with this exponent, and I think this is also used to represent not a number and special numbers like that. But you only got this 23 bits here, and then the sign is effectively used as well. But if we look at some numbers that you can represent with that, let's just get my source code example. So let's say this was the number that the 2 numbers that the GPS module gave us. So let's put these in here on a spreadsheet, which is, this is how many bits we have, and this is the maximum value that can be represented with that number of bits. And if we take the two numbers here that we were looking at for our example there, we see that this one's going to require somewhere between 28 and 29 bits to represent, and the other one, because it's larger, it's further away from 0, it's going to take actually 30 to 31 bits to represent. So neither of these numbers can be represented with the 24 bits that are available to us in the floating point precision, single precision floating point number. It just can't be done. So we're throwing away some of the precision, and how much of it we're throwing away depends on how large the number is. So here in New Zealand we're dealing with numbers like this, where the longitude is quite a bit larger number in degrees than the latitude, like this. So that's why the latitude seemed to be a little bit more accurate than the longitude. And what happens here, if we take this float and we divide it by 10 million, we'll get something actually like that. So I've just made this 6, just to exaggerate the problem a little bit. I've just taken 6 significant digits there, and also this one, 6 significant digits. It's not quite that bad. You don't lose that much precision, because 1 bit of data can represent 2 values, but whereas 1 decimal place can represent 10 values. So just because you've lost 1 bit doesn't mean you've lost 1 decimal place. It's not that bad. But anyway, you'll lose a significant amount of data there. And the other thing that's kind of confusing, I'll just put this bit here at the bottom. If you take this floating point number and you print it out to say 15 decimal places, you'll get a number like that. And this is a bit misleading for newbies, and me too apparently. Just because you don't see the number stop there, like it doesn't go like 000 after that, that doesn't mean that that number is actually an accurate number of high precision. It just means that you're looking at the closest floating point value that could be mapped at that resolution. Anyway, so that was a bit long-winded, but the simple fix is you just do this. You just use doubles instead. That's maybe not quite so simple on some architectures where it slows everything down a lot, but for STM32 that doesn't seem to be a problem at all. So that's all I really had to do. Actually, there was one other thing. I'll just look at the sketches that are running on the S-Bus mixers for this. So now that we have 8 GPSs, I had to drop the speed value. So we're only looking at lat-long satellites and altitude. So I've got 4 values times 8 is 32. So there's 32 floating point numbers traveling down this daisy chain between all of the 4 S-Bus mixers. And I had to change, or I had to add an option here so that as well as the normal latitude and longitude, which is what I was using before, which will give us the floating point number with some precision lost, I added these options so that it would just give you the raw integer value that the GPS was providing, so that you wouldn't lose any precision. Makes things a little bit awkward for the way this system's set up, because each of these nodes outputs a single floating point number. So if I turn this live value on, well, there's nothing connected at the moment, but if there was a board connected, this would be updating in real time, showing us the value. And when you're using this integer version, it just shows you some messed up number, so you can't use this live feedback, but it's going to have to be necessary if we want to get the full resolution of things. So this one here is the first board in the daisy chain. So we've got the 4 values there, or 8 values, sorry. And then this is board number 4, but at the bottom is all the same. And then we just have 24 values coming in from the other modules that have all been passed along. We saw this in the last video, so I won't really go into too much detail about that. It's just that we have 4 boards instead of 3 now. So after making that change, I did just a quick little 5-minute test. The result on the left here is one of the ones from before. This is like, I think, 2, maybe 4 hours of results. The one on the right, I think, is less than 5 minutes at 10 Hertz. So you can see where I've been walking around like this. And when I saw that, I thought, oh, I'm really going to have to do this again properly, aren't I? See, this is how the weather works in New Zealand. 30 minutes ago, I went out there and I put the
test subject on the fence with a bit of plastic over it. And can you believe I was thinking I might not even need to put the plastic over it because there was barely a cloud in the sky, everything was fine, sunny, and then like 30 minutes later we got this. It's getting really annoying. It's hard to find a break of more than about 40 minutes or so without rain. It makes a nice rainbow though, doesn't it? Look at that. Actually, it doesn't look very nice on camera, but it looks quite nice in person. Yeah, so this time, instead of racing out there and trying to rescue it, I thought, I'll just leave it. I'm getting sick of it. I'm just going to see how it rides out this rain with that little bit of plastic on there. Not really holding my hopes up, but I'm just getting so sick of it. We'll see what happens. And the other thing is, I know it's only going to rain for about 10 minutes at most. It's really annoying. It's not proper rain. It's just the rain that comes around to annoy you. See what I mean? 3 minutes later, it's gone. Everything's okay now.
Eventually the weather cooperated enough that I could do a 10-hour test, so that's what we're going to look at for the remainder of this video. This is the satellites used, and the 6M is not picking up really that many. And as we saw in the last video, it didn't really seem to make a whole lot of difference, although as you'll see in the rest of the results, the 6M really didn't perform very well compared to the other ones. This is the altitude. I'm using height above sea level this time instead of the ellipsoid, so that's why it's changed from about 100 and something down to 80. But other than that, it shouldn't really matter too much. And again, the 6M has a few altitude spikes fairly frequently actually. And the other one, what's that one? BN880, also not performing too well in altitude. And since these are on top of each other, I'll separate them out. And I've listed the microblocks modules at the top and then the BN ones at the bottom again. And now we can see, yeah, BN180's not too great and 6M's not too great. All the other ones, not bad actually. Now we have latitude fluctuation. Once again, 6M is probably the least accurate by the looks of it. What's the light blue one? BN220 doesn't do so great in some points as well. And then if we separate those vertically like we did before, now the comparison that we want to make here is with longitude. So this is longitude fluctuation and latitude fluctuation. I'll just flip between these a little bit. But notice that now that we're using the proper precision, they look about the same. Like one of them, like we don't have the situation where one of them is more stable looking than the other. They both look about the same, so that's good. Now that I'm measuring or calculating the distances in meters rather than just showing lat long numbers, I was able to look at the average distance from true. Now the true is what I'm calling the average of every single measurement across the whole 10 hours. And as I mentioned in the previous video, we don't really know if that's exactly the perfect number, but given that we've sampled, I think it's 2.7 million values across 10 hours from 8 different GPSs, I think it's pretty safe to say that this is a good estimate of the true lat long. Anyway, so the average distance from the true for that 8 hours in meters is shown here, and all of these graphs actually, they're separating into two distinct levels. So we've got the M8N, M8P and 7M all perform quite well on the same level or similar level, and then all the other ones are in a different level. So all of the Bayesian modules are not so good, and the 6M is in with them as well. Actually the 6M is kind of worse than the Bayesian modules in a lot of respects. Over here we have the longest distance from true that was recorded during the whole 10 hours. So the M8P does very well here, about 3 meters, and the 6M up to 10 meters away in some cases. Others similar, very similar actually, the Bayesian modules in this one. And then we have latitude standard deviation and longitude standard deviation in meters this time, like not just the lat long degrees. So moving on, we have the heat maps. Now we've got way more resolution in these heat maps this time. And I improved my procedure for processing these results so that I could do this stuff a lot quicker, and much of it was automated now. It's really nice having everything in one file so that I can just hit one command and all of these maps will be generated with different parameters. Anyway, so this, what we're seeing here is a perfect white pixel for any location that was ever measured across the whole 10 hours. And as before, we've got microblocks in one row on the top and base shunt modules along the bottom. And the most noticeable point about this for me is that the 6M is not really at all in the same class as the 7 and 8 modules from microblocks. The base shunt modules are all pretty similar, except the 880s do overall a fair bit better than the 180 and the 220. Oh, and I should mention that the crosshairs here show the average of all of the measurements for all of the GPSs for the whole test. So this is like the true location there, and these little green markers on the graph axis, they are in meters now, and you'll notice they're pretty much equal now. We don't have any elongation. And moving on to the actual heat map, so this is scaled so that the point with the highest value is going to be white in every case. So there should be one point in each of these maps that's pure white, and then the rest of it scales down to black where there was nothing recorded. And we can also see now that we have some kind of vertical lines appearing a little bit in some places, and I don't mind that. I think that's okay. It doesn't seem out of the question that some values would be preferred more than others when it comes to these floating point precisions. But now we do have every pixel shown here is a unique value that was reported by the GPS. Anyway, so these elongations are going vertical now, which also makes sense. Before they were going horizontal, which I think I just mixed up lat long when I was drawing those graphs. But this graph here doesn't really show you much of the full travel of the values that were reported. So I made this other one like this, which is the same as the heat map, except it's lifting the floor of the values. So any point that ever had a GPS recorded is not allowed to be pure black. It has to be, I think, 0.1 brightness. And then all of the values are scaled between 0.1 and 1. So we can still see the heat map, but we can also see the full travel of everything as well. And I think this one's probably, if you were to sum it up in one graph, this is probably the easiest one to visualize what's going on. Okay, we finally got some nice weather, and I've set up all of the 8 modules there with the 6M support now. And I'm just going to do a little walk down there, which I think is about east as I can get it, and then up there. And what I've noticed is that just by holding this out at my arm's length like that, so that the modules are probably about a meter away from my chest, I can turn around like that, and we can actually see the circle that it draws. So let's go. Yeah, I think this should be about east. And I'm not walking very fast here. So the 10 Hertz rate, at least in the tests that I did the other day, was enough to draw a continuous line. So let's stop here for a second, and I'll hold it out as far as I can get it, and we'll just do a nice circle on the spot. Like that. And it seems like even the 180 can keep up. Like, I mean, it draws that circle reasonably well. Oh yeah, and I found, you can do this too. Swing it around a bit. Not a full circle. But let's stop over this little thistle. Unlike the last farm I lived on, there's hardly any of this stuff here. That other place, they really didn't look after it very well. But this farm keeps on top of things. Okay, I'll just stop there because I'm going to come back to that in a minute. And I can like turn around. Stop, and whoops, I'll just go a little bit over here so we can clear away from that spirally bit that I did. And we'll turn this way a little bit faster, and then I'll go back to the thistle approach it from this side a bit and see how well we can stop exactly on there. We're kind of doing that with the point where we put it on the gate anyway, aren't we? Alright, that'll do. Let's now approach it from... Actually, I don't want to don't want to walk over where I did that other circle, so let's just go back to the gate. I think that's good enough. And I am of course going to put the plastic on again, because we saw what happened yesterday. You never know, it could be raining in another... I wouldn't be surprised if it's raining in another 20 minutes.
Okay, hopefully that was a fun little demo. Now I'll just keep that playing and watch as it continues here. There's a couple of interesting things to note. One is that the BN220 and the BN880, after the movement stopped, those two seem to spread away. It's almost like the movement helped them be more accurate. And the rest of the modules, they don't seem to really be affected that much. And in particular, look at the M8P. It's just really sitting there really nice and accurate, isn't it? And just in case it wasn't clear, these little dots that are shown in the trail here, these are the actual measurements that were received for each module, and I've just connected these with lines to show the trail and faded it out over, I think, like 50 measurements or something, 30, I don't know. But you may have noticed that they're not always coming in at equal spacings, and in particular this white one here is a good demonstration of that. So these points here are spaced out more than those ones, whereas some of the other modules are keeping up a much better pace. So this pace here, the one at the bottom there, that's the full 10 Hertz speed, and it looks like the white was only transmitting at 5 Hertz for a while there, but that's not the fault of the GPS. I think that's just to do with the way this daisy chain works. So remember, we've got a bunch of UART connections going all through like that before they get to the SD card, and the connections between each one of these S-Bus mixers is going at 25 Hertz. But the value from the one at the beginning of the daisy chain has to get through 3 other modules to get to the last one. So I think it's just something to do with that timing, that it's just a little bit delayed, or the time that it's getting passed from one to the other, it hasn't quite received the one coming in, or something like that. I think if we were to measure these all on separate S-Bus mixers so that they were going directly into the SD card from the same module, they would all be showing a proper 10 Hertz speed like that one at the bottom. Okay, let's have a look at some plots for that little adventure, and I've taken away the crosshairs in the center because we're not really interested in the relation of this to the so-called true value for the full 10 hours, but I've left the axis markers on the side here, so these are 1 meter markers, and as we expected, those little circles I drew, I was expecting those to be about 2 meters or so, given the length of my arms, and then a little bit extra for that piece of wooden board that I was holding. It's about 1 meter or so, so it seems to match up fairly well with that. And they are nice and circular, there's no elongation, so that kind of confirms that I've got these axis ratios correct. Also down here, nice and circular. And this is the M8P that we're looking at. This is overall by far the most accurate, and we can see that in 2 points. One is that the start and finish location, which was the same place on the top of the gate, is matching up very, very nicely there for this one. And also the fact that the line going through these circles is right in the middle of it, which is exactly how I walked, because I was holding the board in front of me and then I stopped and turned around and did a 360 like that. And also here I did that as well. This point where I stopped over the thistle, we did go back there, but it's not really that easy to tell how well it matched up there. Fortunately, this one here, I wasn't thinking about it at the time, but that point on the gate was a good reference to see how well it goes back to the same point that it was before. Alright, let's have a look at some of the others. This is M8N. I'll just go through these one by one. None of the other ones are even, well, I was going to say not even close, but they are close to the M8P. But they're all off a little bit. Anyway, that's M8N, doesn't quite manage to go back to the beginning. The circles are nice. Then we have the 7M. This one does seem to go back to where it started, but the circles are not so nice. And if we look at the M8P in comparison,
This circle down here in particular is in a fairly different place. Let's look at the 6M. Doesn't go back to where it started. This is looking a bit wonky here. So now we can see this is the point over the thistle where I went back to. So this is the thistle in the second pass. And then I'm not really oh, it's probably here actually. This is the first time I stopped over the thistle. So those didn't even match up for the 6M. Whereas it looks like they pretty much did for most of the other ones. Yeah, so the 6M overall is coming out the loser in this comparison, really, isn't it? BN880, not too flash. I'll just pop the M8P back on again. Like that. Alright, BN220. And I'll just briefly flash up the M8P again as like a reference, because we need to sort of have something to compare it against, otherwise it's just sitting out there in open space. Well, we can see that this doesn't match too great. The spot over the thistle is okay by the looks of it. Circles are a bit off. This is strange, isn't it? Like, we didn't get the line going through the middle of the circle there at all. Like, it's like way off the side. That one's okay. Next one is BN880. Bit of a wonky circle there. Thistle point not quite on, another wonky circle, no match there. This is the one with the active antenna, so I would have thought that this would do a little bit better, considering that it has a nicer antenna. And let's look at the 880Q. Now this one does not have an active antenna, but from what I can see, oh, that circle's a bit wonky, this one's okay. Almost went back there, thistle point looks alright, compare it with M8P. It's actually pretty good. The 880Q did the best of all the Bayesian modules at matching up with the M8P. In fact, I think it might have done the best of all of them. Yeah, I think it did actually. That's kind of strange, isn't it? Actually, there was a comment on my last video saying that the 880 uses the same like engine as the U-Blox M8Ns. And I wasn't sure about that, but now that I look at this, maybe it does, you know? Actually, let's look at the other 880 because that one wasn't so great. Yeah, that's the 880 with the active antenna. Looks like it's done much worse than the Q, which does not have the active antenna. Anyway, so let's have a look at just how these I put them in teams here. So we've got the microblox modules are like red-pink colors like that. They match fairly well with each other, apart from the 6M. Oh, no. Oh, it's the 7M that's off there, isn't it? I was going to say 6M. Huh. Interesting. The 6M's actually not doing too bad there. Oh, no. Then it's over here. It seems like they match in some places, but then they don't match in other places. So it's sort of skewed. The 6M is way off up there. Let's have a look at how well the Bayesian modules match each other. Now, none of these really match each other very well. So for overall consistency, the green team is losing this comparison. And just finally to put them all on, it gets a bit difficult to see, but just to show you what they look like all on the same screen together. Well, that's it for this test. Sorry for the screw up last week, but all we can do is try and fix our mistakes, right? So in this test, we didn't really learn a whole lot about, relatively speaking, which one of these is better. Well, we did see that the 6M is not really that good. I was expecting the 6M to be better, considering that the 7M was pretty good. But it's not really fair the way I did it last time to the modules that do provide very accurate results, because we're taking those accurate results and we're just smudging them around and messing them up. It actually makes the good ones look not so good and the bad ones look not so bad, I think. But overall, the sort of the ranking hasn't really changed that much, I think, from these new results. And the question of which one do you want to use on a radio control plane or a drone or whatever, that doesn't really change that much either. I'd say probably the best all-rounder for the money looks like the M8N. Anyway, thanks for watching, and I'll just let the rest of this thing play out here. I have not actually made this animation yet as I'm recording this voiceover, so I don't know how many hours of animation this is going to be. Probably about 4 hours or so. It's probably not going to be the whole thing because there's a lot of data to process, so whatever it is, I'll just put on the screen how many hours it was, or there'll be a timer showing. Yeah. Thanks for watching. Bye.